But as time went along, I realized there was more to engineering than just those weird boys in Jets Club.
Well, let's get started. This is going to be an interesting experience for all of us, I think. So I know Melanie. We went to college together. We took engineering 131 and 132 together. And that's the extent of, how much I know all three of you. We got to talk a little bit during email, but let me silence that. But to introduce myself, Josh White. I teach electronics, communications, and construction here at Jefferson High School. We have my high school alma mater. John Whiteloff is on with his kids from Benton Central. And yeah, so I was in engineering industry for a little bit. I was in the plastics industry doing injection molding, and I was a program manager for a time. Then I came into teaching, and I'm here at Lafayette's Inner City School. So that's my introduction. We're gonna, I think cadence of things, like when I guess want to do a group ask, we're gonna do Michelle, Libby, Melanie, if that's okay with you guys. So Michelle, if you'd like to introduce yourself, and then Libby, and then Melanie for everybody, then we'll get rocking and rolling.
Hi everyone, my name is Michelle Rodio. I grew up in New Jersey and I went to college in Florida at a school called Embry-Riddle Aeronautical University. I did my undergrad in aerospace engineering and a master's in mechanical engineering. During that time, I worked at Kennedy Space Center for 2 years and I was working on the space shuttle program. So I got to work on processing the solid rocket boosters and help launch the astronauts to the International Space Station. After that, I moved to Virginia to start my PhD in mathematics. And in the meantime, I had earned a master's in mathematics, and just this past May, I graduated with my PhD. And for the last 6 years, I've been working at NASA Langley Research Center, working on a variety of projects. During that time, or in the years in between, I had also interned at various other companies, doing a lot of different projects in engineering. So I have a lot of different project experience on a lot of different programs and research areas.
Okay, so my turn next. Hi everyone, I'm Libby Urig. I grew up in Ohio and I got my undergraduate degrees there at Youngstown State University in mechanical engineering and applied mathematics. While I was an undergrad there, that's when I first got introduced to NASA Langley through their internship program. And I've been working on and off at NASA Langley since 2016 through a couple internships and now through my graduate education work. So I have a master's in material science and engineering, which was obtained about 3 short weeks ago. So very exciting. And I work in the advanced materials and processing branch at NASA Langley, which is focused on what we make airplanes and rockets out of, and can we make it better, faster, lighter.
All right. Hi, I'm Melanie. I grew up in West Palm Beach, Florida, the very southern tip of Florida. I then went off to Purdue, which is in Indiana, and then I came here to Virginia. So I've been a little all over like the eastish area of the states. While I was at Purdue, I studied aerospace engineering. That's where I got my bachelor's as well as my master's, which I just graduated with in August. But I actually started at Langley while I was a senior in undergrad and started as a Pathways internship. A Pathways internship is usually multi-sessions while you're in school. And so what you'll do is you go to NASA, you'll have like basically a work session during the summer or during a different semester, and then you go back to school and you kind of switch back and forth. And so while I was doing that, I was getting experience working on human exploration for Mars and then the moon when we got this new administration and we switched from Mars to the moon. And then when I graduated, I came to work here full time in that same branch. And so now I'm still working on human lunar exploration. I'm working on the human landing system, which is helping make sure that the 3 contractors who are designing our next basically like the next Apollo lander for the moon. Art is designing it in like a complete and safe and risk-averse way as much as possible, and they're considering everything. And so I have like a systems engineering aspect to it, and so that's kind of what I'm working on now and how I got there.
Perfect. Thank you all so much for that. Lots to unpack. Melanie, are you referring to Artemis?
Yes, definitely. So the human landing system is part of Artemis. So the program that I'm working on is actually designing the lander for the very first crewed Artemis mission, which will be in 2024.
Awesome. I'm sorry if this is a little bit delayed on my end. I am writing things down and trying to make things cohesive as far as questions go.
No worries.
So first off, I want to, with everybody involved, whether virtually or in person in any of the classrooms, I have in the chat box of the Zoom call, I have a URL that you can use and share for questions. James, our student moderator, will be jumping in at that final leg of our conference, and he'll be asking those questions. That's also on the board in case you guys can't get that URL anymore. All right, so there's lots of ways we could go about this, lots of questions that I could ask, so some of my biggest questions when I was in high school was the breadth and extent of what an engineer is. When I was in high school, I thought very much so that it was product development, product design, and manufacturing. But I didn't know the extent of manufacturing, what that meant, and the different manufacturing processes that there were. So I kind of wanted to have you guys explore the different types of engineering and technicians that you interface with, and give like maybe a 1 or 2 sentence definition of what that engineer does. And that's maybe a hard ask, and I apologize for that, but hopefully it'll give everybody watching a nice primer of the kinds of things that get done at NASA, not just what you are involved in, but also what is done at the NASA level. Libby, you mentioned that you were a contract worker. You are in the National Institute of Aerospace, and contract work is different, not, that, so there's different relationships that could be had in engineering, right? There's suppliers, customers, contractors, and then the main head honcho, either call it the OEM, call it whatever. But Libby, when you wanted to, when you could speak, if you wanted to talk about that contract work and what that relationship meant, then yeah. So that was a lot, but basically, what engineers and technicians do you interface with, and how would you define them?
You still want to go in the Michelle, Libby, Mel order? Or do you want Libby?
To.
Okay. So having switched all of my degrees from aerospace to mechanical to math, I've actually seen a lot of different types of engineering. The bulk of the recent work that I've been doing has been a lot in software engineering. So NASA isn't just space exploration. We have aeronautics, and we have science, and we have human exploration operations. And I have spent the bulk of my research in the aeronautics research directorate. So I work on looking at the sound, how sound moves around aircraft. And so a lot of the engineering work that I do is related to a computer and software development. So I do a lot of high performance computing work. I interact with supercomputers, not just on our center, but across the entire agency. And then in my work modeling the aircraft inside of a wind tunnel, I work with a lot of the test engineers who will design wind tunnel tests. So the design engineers that I'm working with who want to figure out how sound moves around a specific aircraft, they're going to design that aircraft. Then we're going to work with manufacturing engineers who build that aircraft, who assemble it inside the wind tunnel. Then we have test engineers who then take that model and they design our entire test for us. So although I work for NASA, I'm at a wind tunnel serving as a customer because I'm at the mercy of the test engineers in that facility. And then if anything goes wrong in that test, we have engineering technicians and mechanics who will work and design on that build, and then we'll cycle back through. And then when we run the tests, I'll take the data and I will process that in the computer, and I will use supercomputers, not again like at our center and at NASA Ames in California, and I will send that data to there, and then I will run different simulations and output different results on how acoustic waves move. So in the position that I'm in, I get to see a lot of that. And in previous internships that I had, I was more on the manufacturing side. So there was a little stint I did where I was working at a missiles and fire control facility. And so I was working in the manufacturing lab, building electronics components for missiles for the Department of Defense. And when I was at Kennedy Space Center, I was more on the processing side. So I would help with the technicians there to help build the space shuttle solid rocket boosters. So I've kind of seen a lot of different types of engineering, but the bulk of the work that I've done in the last 5 or 6 years has all been in software development. Because in order to solve a lot of the really heavy science problems that we have in the world today, you need to have a lot of computer processing power. And so being able to use really strong, powerful computers and get the simulations running that you need to have a really good understanding of how the computer works.
Really fast, I want to cut in and clarify a couple of things.
Okay.
So you talked about the wind tunnel test, the design engineers who designed the product. You had your own test that you wanted. So you were mainly focusing on sound and how it interacts around the aircraft.
Yeah.
And then you brought up the technicians and mechanics fixing the product. Does that mean the aircraft or the test itself, the test procedure?
Both.
Okay.
Both. So we have the aircraft. Imagine if you see an aircraft flying, just cut it in half long ways. And so we have the aircraft sitting on the side with the wing up. And so we'll have air flowing over the wing, and we'll put the aircraft in different configurations, and we have microphones off to the side so we can measure the sound pressure on the bottom side of the aircraft, so the sound that essentially the community would hear. So when the aircraft flies above you, we don't really care about the sound above the aircraft, we care about the sound below it, because that's what we on the ground will hear. And so if something goes wrong in the test, there's a variety of different people who work to fix it. So if something breaks on the model, if we have to change the configuration of the model, if something is wrong in the wind tunnel test itself, in the wind tunnel facility itself, just a few weeks ago, one of our duct systems got loose and was shaking really, really badly. And in an acoustic test, any sound that's coming from the duct system is going to really affect our results. So we had to stop the test, and we had to bring in the facilities managers to adhere the duct system. So it's really just a variety of issues of anything that can go wrong will go wrong, and you just need to make sure that there's a variety of people there to help solve the problem.
Okay. Sorry to interrupt, Libby, but if you want to go ahead.
Absolutely. So yeah, I'm definitely a little different than Michelle in terms of the work that I do is a lot more experimental, a lot more hands-on, just as she was talking about a lot of the computational work she does. And so, like I said, I'm a materials engineer. More specifically, I'm a metallurgist, so I'm focused specifically on metals engineering and alloy development, things like that. And the types of engineers I work with, I'd say that there's kind of 3 different categories. There are the engineering technicians who are very specialized in a lot of materials characterization. So there's very specialized methods, materials, stencil test machines, scanning electron microscopes, PMs, things like that. And we have engineering technicians who that is their job, to know the ins and outs of that specific machine and the operation of it and the successful characterization of the material. The other types of engineers we sort of have are the research engineers, which are more focused on, in our branch, for some kind of problem. We want to make an airplane fuselage faster. We want to 3D print this material rather than traditionally manufacture it, because it'll be faster with less waste, things like that. And the research engineers delve real deep into the science of the different alloys. So like an aluminum alloy is a mix of all sorts of different elements, periodic table. And how do we, mix the elements such that the material is going to give us the properties we want, both to manufacture it and then in its final form, life stage. So, and the third is kind of engineering operators, which I guess is similar to the technicians, but we have some very specialized 3D printing equipment, and that requires a full-time operator, actually a couple full-time operators just to run and manage. So.
Perfect. Can I circle back to the research engineers? You talked about designing different things, wanting fuselages that were lighter, faster, stronger, better. So are these research engineers focused? So are these design engineers, or are these manufacturing engineers, or are these metallurgical?
Oh man.
Are they working on the design or specifically the material?
A little bit of all of the above. I tend to, the group I work in is very multi. So right now I mentioned the aircraft fuselage. That is a project under the Advanced Aeronautic Transport Technology Program. So pretty much we're looking at making airplane fuselages faster so that customers like Boeing and like that, typically they make, I believe, 15 planes a month, and they want to increase that all the way to 100 planes per month. And so we have a new manufacturing method that is essentially, I kind of explain it like I'm 5, is we squish Play-Doh into a mold. So we squish metal into a cylindrical shape for that plane fuselage, the tube part that you would sit in. And so we have some people, we have manufacturing engineers who are determining, what the best way to squish that metal is. We have, manufacturing and processing engineers there. We also have physical metallurgy engineers who are focused on, okay, what is the best type of aluminum specifically we're looking at? What is the best aluminum alloy to squish and retain the properties? We also have design engineering of, okay, well, we've never squished an airplane tube. How do we design it for load cases? How thick does the shell need to be? How thin can we make the stiffeners? How light can we make it? What's the loading going to look like when it's flying and things like that? And I'd say it's about a 25-person team. So of the 25 people, there's probably 2 or 3 people on each one of those categories.
Perfect. Thanks for following up on that. Melanie, same question.
All right. Well, the first thing I wanted to say is that, Josh, I really resonated with what you said, that when we went to when I went to college, at least, like, I was just trying to figure out, like, even though I'd selected this aerospace engineering, what does that really mean? And I think it's really fun to hear about how different it is, like in Libby's field versus in Michelle's field, and in my field as well. And even within aerospace engineering, there's just so many different there's such a wide range of different jobs that you can have. And it's worth pointing out too that all of these different people work at NASA. The NASA workforce requires such a wide range of people with different experiences and knowledge sets in order to make it come together. And I mean, it's all of those people to make space exploration happen, all those people to make material science and aeronautics happen. And so I just thought that was worth pointing out. And it's just really interesting hearing from those people. But to bring it back to what I'm doing, I actually didn't know my job existed until I got the job. When I was in school, I was mostly focused on propulsion, which was for me rockets, but what I actually do now is systems analysis. And so what that means is that out of the 50 or so people in my branch, we know a little bit about a lot of things. So I know a little propulsion design, I know a little trajectory design analysis, I know a little bit about how to select which elements should be launched on which vehicles and in which order, and because that impacts a number of things like the timing and how much propellant will boil off in space and the alignment of the planets. You know, it's just like a lot of things get put together in order to design a space mission. And it's also, to some degree, why are we doing the mission in the first place, and what types of vehicles do we need in order to accomplish that why. And so my branch, we work with a lot of people at different centers. We work with a lot of people from J.F. Johnson Space Center in Houston, which works on designing specific habitats for the astronauts. We also work with Marshall Space Flight Center, who work on designing the rockets. And then we also respond to requests from headquarters. And so kind of my whole branch would do the same thing, is they're just working on a lot of different little pieces at the same time. So it's the primary people I work with, but you know, also I work with like the other people at the centers, and you know, they're all aerospace engineers or mechanical engineers or mathematicians or different types of engineers at those different centers. And then of course the people at headquarters, this is, you know, later down in your career, but you might have started as something like a mechanical engineer or an aerospace engineer, and you've worked your way up, and then you became a technical lead, and so you oversee a lot of people, or now you're like an associate administrator for human exploration. So all kinds of people that I interface with, and that's all part of systems analysis and systems engineering.
So if I remember right, your master's specifically was in something called System of Systems.
That's right.
So, I mean, that may be a whole other thing to unpack. But I did kind of want to shift into this question of, all three of you have obviously done the thesis process. Libby, your most recent, congratulations, it's awesome. But I think I kind of want to go backwards, Melanie, Libby, and then Michelle, because Michelle, you're at the doctor level, so you're kind of the guru here. But Melanie, do you want to talk about maybe a little bit what System of Systems means, and how it ties into your job that you thought didn't exist, but also the process itself, like. So there's school, there's high school that everyone in here watching or is either teaching or involved in. And then there's technical trades, there's college levels, there's associate levels, and then there's this master's level that you all have decided to move on into. And then there's masters, and then there's thesis masters. And so what does that thesis master get you, and what does that process look like?
Sure. So just to briefly start with the first question, what is a system of systems? And so I mentioned that there's a lot of different pieces that go into a space mission. And so that's the launch vehicles, the rovers, maybe there's like an extra rocket, we call it an in-space stage, which is just the in-space portion, not the launch vehicle. There's the crew itself, there's maybe satellites in orbit, relaying communications. And so all of those I think are systems. I know they're systems on their own, and they have some degree of operational and managerial independence, as well as they're all geographically distributed. However, they're all working together to achieve a higher level purpose, which makes them a system of systems. So that's just a brief description. And so how I came to studying that in grad school was as I was a student in undergrad, I had the Pathways internship that I talked about in the beginning, which was coming back and forth between school and NASA and learning more at my work experience, and then connecting that to what I was learning in school. And then I realized that I just didn't know enough. You know, like it was senior year, I was taking these really interesting classes, but I was like, the people I work with, they know so many things. And I want to know more. So to me, choosing a master's was just committing to 2 more years of school to take additional classes and come out with that much more experience. It also did give me a slight pay raise, but I wouldn't say that you couldn't have gotten that same pay, promotion eventually after just some years of experience. So it's not like you couldn't have gotten there. Obviously, people, they go the whole time. But it was like that twofold reason for me. It was learning more and having like the promotion maybe slightly quicker than I would have otherwise. And so then the thesis process itself was you either choose to do a non-thesis master's or a thesis master's, at least in my college. And a non-thesis master's would have been great too. It was just taking more classes, but I chose to do a thesis because you swapped classes for graduate research. And I chose to do research in systems of systems engineering because I found that really relevant to space systems in particular. Obviously, I really like space. And I just thought that systems of systems was really cool after talking to the professor about it. And so that's just how I came to that conclusion.
Awesome. Libby, go ahead.
Absolutely. So you mentioned kind of the career path starting in high school, and similar to Melanie, I kind of just wanted to make an anecdote about high school into that transition into undergrad and graduate school and whatnot. So in high school, my school had JETS Club, Junior Engineering Technical Society, and it was exactly what it sounds like, and we did a lot of bridge building competitions out of balsa wood, the Lego Mindstorm vehicles, programming those and having them run different obstacle courses. We made little rockets out of like toilet paper tubes and things. And while I really enjoyed the club, I had actually left after 2 years of being in there going, I am never going to be an engineer when I grow up, because I was one of very few women and the people were just very weird. And so I said, this cannot possibly be the field for me. And so I got to undergrad, and I actually started undergrad as a chemistry major, a little more into the pure science aspect of it. But as time went along, I realized there was more to engineering than just those weird boys in JETS Club. And that, I actually enjoyed the subject quite a bit. And so through undergrad, I kind of got my foot in the door in graduate school, actually kind of through happenstance of working at NASA Langley. So I was lucky enough to get an internship. And so this is back into your child question. And we will pay for it using a contracting company if you want to get a little bit more specialized education. And so I took that opportunity. And moreover, I knew I wanted to go on for graduate school even before the opportunity came along, just because for me, I was particularly interested in this material science subfield, and that's often not a bachelor's level degree. Typically, it's a specialized field. You can kind of get minors and things like that, but so just to tie briefly, I know you wanted me to bring up the contract work very briefly. I am by no means an expert in the subject. I am, a lowly contractor. I don't necessarily have the hierarchy of how they interplay with each other. But at NASA Langley, there's a number of different subcontractor entities. There's Jacobs, AMA, NIA, which is the one I'm involved in. And essentially, they're all just different pathways to work on center, work in the facilities. Each one does kind of have its own little bit of a specialty or whatnot, but I guess the thing that I would want to highlight with that is that contracting work, don't assume that the only way you can work at NASA is through a civil servant position like Melanie and Michelle. Not gonna lie, I hope to get a civil servant position eventually, but I still get to sit at a desk at NASA, interface with all the wonderful colleagues there, work with the equipment there. My paycheck just comes from somewhere else. Oh, thesis creation and defense process. Like I said, it was proposed through my supervisor at NASA, and she already kind of had a topic she wanted me to look into, which was additive manufacturing of magnets, kind of. There was funding for it. There was an interest for electric motors, electric axial motors. And so I've spent the last 3 years on doing the coursework and thesis work somewhat remotely because I was staying working at center. So I took my classes through UVA, which is about 2 hours away from center where I work. And so commuted back and forth or did stuff online until eventually I had written a thesis in a pandemic. Everything's great.
Super, super kudos to you. That is, is awesome. Yeah, Michelle.
So my story is actually, I think, quite a bit different. I grew up in a really small farm town, and I didn't even know what the word engineer was until I took AP chemistry in junior year. Math was always like my subject. I was really, really good at it. I was good at science, but I was great at math. And I didn't know what I wanted to do when I went to college, and I was talking to my chemistry teacher, and he suggested I be an engineer. And no lie, the words out of my mouth are, what is an engineer? I had no idea. My parents hadn't gone to college. Everyone in my town was a farmer. So I didn't know what that was. I didn't have the exposure to know that there was all different types of things that you could do. And I thought that had I just majored in mathematics, that all I'd ever be able to do is be a math teacher. And I really wanted to work for NASA. I didn't compute that I could study math and work for NASA at the same time because I didn't have the concept to know what degrees could give you what opportunities. And so I went at home and I think I used Ask Jeeves because I don't know if Google was a thing when I was in high school. And I researched what astronauts did because that's what I wanted to do since I was in 5th grade, was be an astronaut. And I didn't think that I could study math and be an astronaut. And I noticed that unless they were in the military, they were all aerospace engineers. So that was what I chose to major in without having any understanding of what an aerospace engineer did. And when I went to undergrad, I enjoyed it, but I never really saw the passion that I wanted to see because I was always looking for numerical work. I liked to do the mathematics. And so when I was a junior, I ended up getting a job at Kennedy Space Center to work on the Space Shuttle solid rocket booster, which I think, oh, it's right behind me, which is this system here. I should have picked this up earlier, but I was working to process the solid rocket boosters on the side. And I would have stayed there. I really loved that job. It was amazing to work on the space shuttle program. But when I was a senior in college, the program was canceled. And all of a sudden I was about to graduate and go into the workforce. And the job that I had wanted to do didn't really exist anymore. So I decided to enroll in graduate school. And I was a little afraid of staying in the aviation industry because I was nervous that there would still be no jobs when I finished my master's degree. So that was when I chose to do a master's in mechanical engineering. I originally was not going to do a thesis option. Like Melanie had mentioned, you just take extra classes. So at my school, it was 10 classes for non-thesis, 7 classes with your thesis. But I started working on a project actually making biodiesel for the university. So just another type of engineering. I had worked to build a processing facility on my university campus to recycle the cooking oil from our cafeteria, and I would process that and convert it into biodiesel to run the lawn equipment at school. And after a year and a half of doing that, I just clicked. I said, well, clearly I've been working on a thesis for the last year and a half, so I might as well just do that. And so for the thesis, you write a book. Essentially, you write a report. And so this is my thesis. And so like in it, you just have like all the work that you did over the last year and a half, and you stand in front of your thesis committee. Every school does it a little bit differently, but it's typically 3 to 4 people, and you present your work. For a master's thesis, it does not have to be original work, so it can be work that someone else has done before, and you present it, and then your committee asks you questions, and they judge how well you understand the material. and they either do a pass fail and it's like, yes, congratulations, you're done, or no. But normally when they say no, they give you feedback and they say, here's what you can work on, and you come back and you fix it, and then you'll represent, and then you'll be done. That doesn't happen very frequently, but it's just like a cycle back to make sure that you have enough done at that point. But during my master's degree, I took a graduate level class in mathematics, and that was really where my passion reignited for math. And I said, okay, this is really what I need to be doing with my career. I need to be taking more graduate level classes in mathematics. So my very first semester of graduate school, I knew that I needed to get my PhD in math, and that was where I needed to go. And so after doing 4 years undergrad, 2 years master's, to really just verify that that was what I wanted to do, because a PhD does take a lot of time, I took a year off, and then I enrolled in my PhD coursework. That took me 7 years just because I had switched degrees. But although I was in school 7 years, 13 total between undergrad, master's, and PhD, it was like I blinked my eyes and I was done. Like, I feel like I was just in high school. It went by so fast. But for the master's thesis, it's a little bit different. So in order to become a PhD candidate, every school, again, does it a little bit differently. And even within the school, the departments do it differently. But you typically have to take what's called a qualifying exam. And so I had to do 80 credits of coursework. So my master's was about 30, but PhD is about 80. About halfway through, you take an examination through the university. Either it's oral, so they'll ask you questions. You have to write stuff on the board. My test was just on paper, so everyone does it a little bit differently. And you need to pass that test in order to proceed into candidacy, is what we call it. So if you don't pass that test, that's it. You're not gonna get your dissertation. You won't get your PhD. But once you take your candidacy exams, then it's 3 to 4 years of research after that. And then you get to write another fancy report. And so for your dissertation, differently than your master's, it needs to be original work. It's never been published before. So it's completely original. It's work that you've done, and only if you've done, you're the expert on it around the entire world. You present your research. Typically it's done in front of your thesis committee, friends, family, etc. But as Libby had mentioned, this is the time of COVID, and my thesis defense was scheduled on the very first day that my school closed. So the very first day of the COVID cancellations, March 23rd, I defended online. And at this point, we had no idea how any of this was going to work. So it was really, really interesting. But I actually am grateful for it, because if I had done it in person, maybe 10 people may have attended, but having done it online, I had friends, family. I had a friend in Paris attend. I had a friend that I had just met that week from Zurich attend, because at the beginning of COVID, everyone's like, let me support each other. And I made friends with another PhD student from Switzerland. And so she attended. And so I had about 40 or 50 people on there from around the world, and it was a really, really unique experience. But because it was original work, my work is now copyrighted and it's available at the Library of Congress. But typically most PhDs are like that, just because it's original work in order to get those. But the defense process is roughly the same for master's or PhD.
Thank you guys so much for walking us through that. And it's an amazing thing that you guys have done. Libby, Michelle, you've both discussed the sort of different clubs and opportunities that were presented in high school. My alma mater, Ben Central, which, and this will be put together as a video later for people to share, but my alma mater was a farm county as well, and we had one high school in the area, and still do. So there will be many different demographics that we hit in this last question before we move into the student moderated section. So if you had advice for this variety, this plethora of demographic, what would that advice be? So we'll go back through Michelle, Libby, Melanie, and then after Melanie's done, I will introduce James, and then James will take over.
So I would say find what your passion is. My passion was math, and I was afraid to pursue that when I was 17 years old and was going to college. And I'm very grateful for the path that I had taken, but after 10 years or so, I found myself back to the thing I was the most passionate about in high school, which was mathematics. So find what you're passionate about, and whether or not your school has different opportunities. My school did not have a lot of different clubs and programs. We didn't have FIRST Robotics. We didn't have a lot of these different things. It was a very small farm town. I think my town was 12,000 people. Find what you're passionate about and stick with it, and really take classes and go to the library, get books that you really love, and just teach yourself and learn new things, and you'll get to where you want to be. And just remember that there's not one path to get there. You can go a straight line, you can go backwards, you can turn around, circle around, but you'll always end up where you want to be if you're always following your passion and doing what you love.
Yeah, I have to say, I agree with Michelle as far as the passion goes, and kind of what she touched on at the end. And my key bit of advice is it's okay to not know exactly what you want to do. You know, like I said, I thought I was going to do chemistry. And oddly enough, I didn't mention this part, but the thing that sold me was just a simple presentation. They were describing the College of STEM, science, technology, engineering, and math. And they were like, okay, here's science, here's math, engineering connects the two. And I go, huh, I want to go there. And, you know, I also didn't expect to end up working at NASA. I didn't grow up, you know, at 10 years old going, I want to be an astronaut. This is where I'm going to go. This is the dream. To be honest with you, I didn't think I was smart or capable enough to be. You know, my ambitions were a little bit lower, but, you know, I applied. You know, you don't know unless you try. And so if you apply, and just be flexible to what life might present you with. Like I said, I got an opportunity in my first internship, and that's what's taken me and carried me along for the next 4 years, the past 4 years. So it's okay to not know what you want. You got time to figure it out, and be flexible. Follow the path of, yes, you know, as Michelle was saying, what you're passionate about. But don't get locked in on, okay, this is my 10-year plan. You know, this is what I'm doing every year of my life for the next 10 years. And then the last little bit of advice is try not to take out very many student loans if you can manage. It's okay to go to like a less name brand school if it's not, you know, quite as much money. Well, at least that's what I did. Make sure it's ABET accredited though, if you do engineering. That's the one bit. All right.
Cool. Okay, just to bounce off of what Libby said, so many great things, but I love the idea that you can even know what you want to do, but not know where it's going to take you. And that's just going back to what I said before about, like, I didn't know that systems analysis as a job existed. And that's because, like, there's just so many different, very specific jobs. And it's just like, you may love what, like, one specific thing and know you want to do it, or you may not really know. And so if you know what you want to do, just kind of, or even if you don't, I would say I would advise you to be open to new experiences and to really put yourself out there. And then don't give up on yourself. So you want to put yourself out there. Maybe you want to join new clubs. Maybe you want to join jets. Maybe you don't like jets, as Libby was talking about. I myself joined like a Lunabotics team in college, where we were designing robots. I didn't like that, but I got some experience, and then I was able to talk about being able to just work as a team and being able to do the research to find out all the things that I knew nothing about robotics. But, you know, like, I was able to talk about my experiences there, and that led me to new experiences, and that eventually led to my job that I have today at NASA. And so I was like open to that new experience. And then I'd also say you don't give up on yourself. So when I was in that team, when I was in a couple of different design teams through college, I was kind of in them. I was kind of like, no, I don't like that. Try this other one. No, I don't like that either. I felt a little bit of like an imposter. I think that especially a lot of women feel an imposter syndrome. And I just wasn't sure that, you know, if I didn't know these things, maybe I'm not supposed to be here. Maybe like this is just not right. You know, maybe like this is not what I'm for. You know, stick with it. And, you know, you'll learn, you'll get experiences, you'll gain the confidence, and, you know, things will work out in the end. And that's my advice.
Perfect. Thank you all so much. James, if you're ready, then we'll rock and roll. So how we're going to do this, James is going to ask a question, and until the hour wraps up, I think we're just going to do whoever wants to answer it, and then we'll go on to the next question so that everybody gets a variety, if that's okay. James, take it away.
So first question I have is, what does a typical day look like for you?
I'll jump in. So it's COVID. We're all teleworking from home. I think all of us have had to find places in our house that weren't designed for us to work here 40 hours a week or more. It's definitely been a little bit of a struggle, but basically I wake up, I try to do something before I get to work. I find my motivation really low in the morning. So sometimes I'll go for a walk. Sometimes I'll play with my cats. I don't know, just find something to do. And then I have several meetings throughout the day. And then in between times I will work on various projects. So it's almost like if you imagine just a really big homework project. That's kind of my job is. I just kind of pick at it and pick at my to-do list during the day until it's 6 o'clock, and then the day's over. So you get to go sit at your computer doing something else or do whatever.
Okay, so anyone else want to take a shot at that, or?
I'll add something just because I'm going on to work sometimes. When I go into work for the wind tunnel testing, we have a strict operation schedule from 7:30 a.m. to 3:45 a.m. So we'll go in there, and because it's COVID, we of course wear a mask every time. We have to badge in and out of our buildings. But assuming this is regular time, not COVID, we would badge into our building. We would sit down. We would run the test, collect data. And we would do that for 3 hours or so in the morning, and then there's a mandated lunch in the middle of the day for 45 minutes, just because of the way that the facility is set up. And then we run for 3 or 4 more hours in the afternoon, and when the test rests up, I spend an hour or two processing the data, and then it's that on repeat. So.
Okay, the second question I have is, how long does it usually take to design a rocket at NASA?
Mel, do you want to take that, talk about building it?
Sure. It's such a long process. So it's years, decades, I almost want to say, because there's the whole process of do you need a new rocket, or can you use an existing rocket? And then, or can you use an existing rocket but modified? And once you can answer that question, then you have to answer, and that's all wrapped up in the why. Why do we need this rocket? And so that might take 5 years. And then you have to determine, okay, well, what are the design constraints we want for this rocket? That could take more years. And then, so NASA actually follows this phase process for any technology development. And so it's all about the why and what do we need is in pre-phase A. And there's phase A, which is the whole concept design. And then there's phase B, C, and D, which is all the way through developing the technology, making prototypes, doing testing, redesigning, doing more testing, doing some maybe demonstrations. For rockets, they'll do things like the green run, which is what NASA's doing with the Space Launch System right now. They've been doing it for the last few months. It's just a series of tests where they run the rocket at different durations. And then after those testing, maybe they'll do some other integration opportunities. Maybe they'll do other testing like vibration testing. And this all takes many years and a lot of collaboration between different centers. And then they might do a flight demonstration. So that would be our Artemis 1 mission, which is coming up hopefully next year, at least in the case of the SLS, the Space Launch System, which is our big new rocket at NASA. And once it's demonstrated, then maybe you use it for the full mission. So it's a very long process.
Yeah, and then for the build of it, it's not a very quick thing either. So I'll just very briefly go through the space shuttle. So this is the orbiter back when we were flying the space shuttle program. And so this would be built in one facility called the Orbiter Processing Facility. The external tank, which is this large piece in the back. This would be built, I believe, in Mississippi or Louisiana. Forgive me, it's been 10 years since I worked on this program. But so this would come in by barge, and it would get shipped to the Cape Canaveral area in Florida. And then the solid rocket boosters, these would get built in pieces. So this would come in a piece like this. And then each of these little pieces would come in little segments. And so these would get shipped via train, I believe, from Utah. But again, they came across the country to get shipped via train, and we would have to check them when they came in. And so this whole process took several months. So by the time that you would get our AFSCR, and we would add all these segments and we build them, which is the bulk of what that work that I was doing, that would take several months to build the whole thing. And then you'd have to do leak checks to make sure that all these were assembled correctly. Then you'd have to install pyrotechnics in between the boosters and the external tank, pyrotechnics between the orbiter and the external tank, and on the bottom of the launch pad. And so this whole process could take several months at a time before it's even launch ready. So it's a very, very intense process.
What was your biggest learning moment at NASA?
If I could take this, for me, it was realizing, Michelle kind of touched on it a little bit with the PhD, that you are expected to be an expert in this very small field or whatnot, but kind of the realization that, you know, and I mentioned this earlier, maybe just a little bit of imposter syndrome and not sure if I fit in at NASA. It's intimidating when you walk in on your first day and you're like, wow, I am in the building that does spaceships and airplanes, and realizing that everybody working there is also human and they are experts in this very small, narrow field. But, you know, we all have our different strengths and weaknesses. And so kind of realizing that it really is just like any other workplace was kind of my biggest learning moment. And it got some of the new hire scaries out of the way.
What do you think about private companies contributing to space travel?
My personal opinion here is that it is absolutely necessary. And I think that NASA has spoken, like NASA leadership has spoken a lot on this. It's a partnership, and NASA cannot do it alone, and nor can the space companies do it alone. So we have people like Elon Musk, who are amazing leaders because they are inspiring people and they are getting the vision out there into the public, and they're gathering support. You know, we're all super excited when Elon talks about sending 1 million people to Mars the next 100 years. Like, that's so exciting. But the reality is that we have to work together, and NASA has spent decades and decades contributing to technology development that SpaceX needs, and we fund SpaceX's projects, and that's true of so many different companies in the space industry, and that's true of aviation too. So aviation, actually, the commercial aviation industry started with very heavily subsidized by the government, and it was the government developing these new airplanes, and now it's this, you know, like diverse industry where people can buy their own planes, they can travel across the world. And so, you know, of course, the goal, I think, is where commercial companies will take over eventually, but right now it's definitely a public-private partnership.
What courses do you suggest taking in high school if someone wanted to work at NASA?
Science and math. But honestly, you don't necessarily need to be an engineer to work for NASA. We have photographers, we have lawyers, we have finance, we have videographers, we have people who do editorial. So any class, if you want to work for NASA, there's tons of jobs opportunities, because just in the engineering world in itself, like, you have the test engineers, the research engineers, the software engineers, etc. But we can't coexist without our legal team, without our finance team, without our human resources team, without our business team. All of these things coexist together for NASA to be prosperous. So anything. If you want to be an engineer, math and science. If you want to be a photographer, art classes. If you want to be a lawyer, take classes that will lead you to law school. And any of these jobs or any of those majors can bring you to a position at NASA, not just engineering. Melanie, that's probably more you question.
I don't know. You worked on the solid rocket boosters. Do you want to speak on that?
I think for us to go farther and deeper into space, not necessarily with human exploration, but robotic exploration, we need to explore other modes of energy. Solid rocket propulsion is not the only option. I think there's a lot of different viable ways to launch rockets and explore the solar system. So I think it's going to be beneficial for the research engineers and the design engineers to utilize and think of different ways of travel, nuclear, for example. But of course, some ways are going to be more safe for humans and some are going to be okay for robotics. So just because we can do it for robotic exploration doesn't necessarily mean that's viable for human.
Yeah, I'll add that like many things, there's pros and cons to both approaches. And so solid rocket boosters have a lot of benefits of them. They're really low risk ways of storing rocket fuel and also of low risk just to know that your rocket's going to work. But like Michelle said, they aren't the best approach when you're trying to go farther and deeper into space. So I think it's not whether they have a place, but where their place is, I think.
Thank you all, guys. This was an amazing experience. I really enjoyed learning from all of you guys and meeting you. And yeah, you shared a small nugget of your lives, and it meant a world to all the students that are watching and will watch in the future. I wish you all the best. It was a pleasure talking to you guys. Have a great rest of your day and have a great rest of your week.
Yeah, thank you so much, Josh, and thank you all for the questions. Thanks for having us.
Yes, thank you.
Just to
Sincere
echo, thank you.
appreciation from BC. Bye.
All right. Bye, everyone. Happy holidays.